not going to be like this, right? Got to be transported differently. Now, CO2 is more soluble than oxygen. So some of it can be carried just dissolved as CO2. So for CO2 transport, we can carry a good bit of it dissolved in plasma. I'm going to give you some, I don't know if these are exactly the values that are in your book, but I'm going to round things off, but it's going to be close enough. About 10% of all the CO2 we carry, we can just carry it dissolved in plasma as CO2. Anything above that, it would begin to form these little bubbles again of CO2 gas, and we don't want that, right? We actually carry some of it bound to hemoglobin. So not only does hemoglobin carry oxygen, hemoglobin can carry carbon dioxide. They don't compete for the same active site, so it can carry both at the same time. So there's no impairment of the hemoglobin's ability to carry oxygen if it's carrying CO2 already. And we would call it, that's about 20% of the total amount of CO2 we carry bound to hemoglobin. When we carry it, it's called carb amino hemoglobin. So carb amino, the carbon dioxide is carried bound to an amino acid, not a heme group on the hemoglobin. So carb amino hemoglobin. I just abbreviated hemoglobin. Okay. That's about 20%. What does that leave us with? 70% as bicarbonate ion. What's bicarbonate ion? HCO3 minus. It's the conjugate base of what? Carbonic acid. So look what happens. By the way, this happens also in a red blood cell. So in erythrocytes is where this chemistry occurs here. If you have carbon dioxide in water, always present in the bloodstream, right? CO2, yeah, because you're absorbing it. Water because of plasma. If this is inside a red blood cell, CO2 is going to be in there because of diffusion, water because of the cytoplasm. When these two come together, this is carbonic acid. All I did was just marry the two of them together. That's carbonic acid. Now that will occur. That's an inorganic reaction, however. It requires some energy. We would want to have, again, the lowest activation energy for this reaction as with any reaction. So what should we have that helps us catalyze this reaction? An enzyme. So the enzyme is called carbonic anhydrase. So this is the chemistry. So if CO2, carbonic anhydrase is actually present inside of red blood cells. So if CO2 diffuses into a red blood cell, which it would, in the presence of carbonic anhydrase in water, you will get carbonic acid. Now what do acids do in water? They dissociate. We never get to the second, what do they call them, pKa or something like that, I don't really remember. It's going to do this, right, plus this, there. You okay with that?
No.
Makes sense? And this is bicarbonate. And this hydrogen ion right here is going to go over and get stuck on hemoglobin. Like that. Why is it important that the hemoglobin, or what's the significance of the fact that the hemoglobin carries the hydrogen ion? What are we preventing? A change in what? pH, right? So if we didn't do this, what's going to happen to the pH of my blood when I do this reaction? It's going to become incredibly more acidic. So this prevents that from becoming acidic. And I'm left with the conjugate base. Now, why is it nice to have that conjugate base floating around in my bloodstream? It is a buffer. Yeah, it's a buffer. So it is going to buffer against what kind of pH changes? Acidic or basic? Acidic changes, right? Because if I put something in there that tries to increase the concentration of hydrogen ions, this is going to grab a hold of them. So this is a buffer against acidic changes. And that's important because what are you more likely to ingest? Acids, right? Acids, right? What's your body produce? Organic acids, right? So it's important to have these buffers. So this bicarbonate buffer system is brilliant in the standpoint that it lets me transport CO2, but it also helps me prevent acidic changes in my body. Now certainly, if CO2 levels got really, really high, that's bad because I can't carry all of the hydrogen on my hemoglobin, and so I would get what we call acidosis. And that would be what we call respiratory acidosis. So if my ventilation rate fell, so I'm not breathing as much, what's happening to my oxygen levels, up or down? Down. What's happening to my CO2 levels? Going up. And as my CO2 levels go up, this chemistry takes place, and if CO2 levels are really high, I get a bunch of this, and I can't carry all of that. Okay? So my blood becomes more acidic. And we'll talk about, when we talk about acid-base balance more fully, we'll tie it in with the urinary system, because there are two ways that you really regulate pH, your urinary system and your respiratory system. So we'll put this together with that in that story when we talk